and welcome back. My name is Lekha Sapers, and I'm the author of Rhode Island Computer Museum's Data Storage Series, a grant partnership with the Rhode Island Council for Humanities. This podcast, concurrent with a series of blog posts, is an exploration of miscellaneous data storage technologies from its most primitive era till now. To learn more, visit the Rhode Island Computer Museum website at ricomputermuseum.org. For my blog posts, visit that same website and search for data storage when prompted. But for more about me, visit lekhasapers.github.io. Again, this is Lekha Sapers, and let's get started today learning a bit about bubble memory. The origins of bubble memory trace back to the late 1960s, a period marked by intense experimentation in magnetics and materials science. Researchers at Bell Labs and other advanced research institutions were investigating the properties of magnetic garnet films, synthetic crystalline materials engineered to exhibit favorable magnetic behaviors. Under specific conditions, they discovered that thin films of these garnets could host discrete, cylindrical magnetic domains that behaved like particles. These domains, quickly dubbed bubbles, could be generated within the plane of the film by applying carefully orchestrated magnetic fields. Each of these magnetic bubbles represented a bit of information, either a 1 or a 0, depending on its presence or absence or binary character. This seemingly simple principle held profound implications. Unlike magnetic tapes or spinning disks, bubble memory had no mechanical parts. It was solid state, meaning that it could, in theory, achieve higher durability, lower energy consumption, and longer operational life. Moreover, it was non-volatile. Data persisted even when power was removed. In an era when most computing systems still relied on core memory or nascent semiconductor RAM, this promise was radical. By the early 1970s, prototype bubble memory devices began to emerge from research labs. Engineers demonstrated the ability to circulate magnetic bubbles around closed loops using moving magnetic fields, usually created by current-carrying conductors or rotating permanent magnets. These loops formed the basis of memory arrays. The precision required was formidable. Bubble generation and propagation depended on a highly uniform film quality, stable magnetic environments, and extremely tight control of temperature and external interference. But the technology worked, and its potential became impossible to ignore. The U.S. military, NASA, and other organizations with mission-critical computing needs were early supporters. Bubble memory's immunity to radiation, resistance to shock and vibration, and low power draw made it well-suited to aerospace and defense. At the same time, commercial interests began to stir. Companies like Texas Instruments, Intel, IBM, Hitachi, and Fujitsu entered the field, some motivated by the prospect of replacing magnetic core memory, others by a broader vision of university-reliable, maintenance-free storage. Throughout the mid to late 1970s, development efforts intensified. Multiple fabrication methods were explored to scale production. Engineers refined the materials, yttrium iron garnet, and later substituted variants. To enhance domain stability and mobility, new access methods were devised. Shift registers, detection coils, magneto-optical readers, bubble memory circuits began to incorporate error correction logic and interface controllers. By 1979, commercially viable products began shipping, albeit at limited scale. Intel's Series 7110 bubble memory, for instance, was aimed at industrial and embedded systems. It offered capacities in the range of 128 to 512 kilobits. Modest by today's standards, but impressive for the time, especially considering its robustness. Despite these milestones, bubble memory never broke into the mainstream computing market. Semiconductor RAM was improving rapidly. DRAM chips were doubling in intensity every 18 to 24 months, following a curve that would later be codified as Moore's Law. Meanwhile, fabrication of bubble memory remained expensive and complex. Yield issues persisted. Each chip required intricate garnet film deposition or non-standard substrates, which proved very difficult to scale. Performance also lagged behind DRAM in terms of access time and speed. making bubble memory a poor fit for general-purpose computing. Nevertheless, the technology retained a foothold in critical systems. Certain data loggers, industrial control systems, and aviation electronics continued to adopt it into the 1980s. Its ability to retain data without power and operate in harsh environments made it particularly attractive for systems that needed reliability more than speed. In 1986, the IEEE honored bubble memory as a milestone in electrical engineering and computing, recognizing its significance even as its commercial relevance was fading. By this time, DRAM and EEPROM had captured the memory market. Flash memory, developed in the early 1980s by Toshiba, was beginning to show promise as a faster, denser, and cheaper non-volatile memory. Bubble memory's strengths, radiation resistance, shock tolerance, low power, were no longer unique enough to justify its cost and complexity. By the early 1990s, bubble memory had effectively vanished from the industry. Some legacy systems continued to rely on it, particularly in aerospace and defense contracts, where redesigning around new memory standards was very expensive. But for the most part, it passed into technological history. And yet, its influence endured. Bubble memory represented one of the first serious attempts to commercialize a non-volatile solid-state storage medium. It challenged the dominance of moving part memory, laid the foundational work for magnetic space data handling, and helped catalyze the push for compact, rugged memory solutions. Its development pushed forward our understanding of magnetic domain manipulation, principles that would later be refined and re-emerge in technologies like MRAM, magnetoresistive RAM, and racetrack memory. Today, bubble memory is largely a historical artifact, but its brief arc, from laboratory novelty to niche industrial product, reflects a broader truth about computing history, that progress isn't always linear. Many technologies once considered dead ends later become stepping stones, their ideas reappearing in new contexts and forms.